So let's take a look in a little more detail about a special effect that happens when light goes from a material in which it travels slower into a material in which it travels faster. So the light is going to try to speed up as it leaves the material. We already did this in lab, and we had water and air, and we saw that when the light went from the water into the air that the angle got bigger. In this case, it went from about 40 degrees to almost 60. I hope you realize right away that since the angles are getting bigger, we're eventually going to reach a point where the angle gets too big for it to actually leave the material. So let's take a look. We're going to start with an incident angle of about 7, and we get a refracted angle of almost 10. Not that big of a difference, a change in less than 3 degrees for the path of the light. But as we make the starting angle bigger, the amount of difference between the two becomes larger and larger. And at some point, you'll see that the refracted angle gets too big and the light cannot leave the material. So at this point, you can see that 100% of the light that was heading toward the boundary between the water and the air reflects back into the water. This is what is known as total internal reflection. There is no refraction because the refracted angle is too large. Okay, so if we have light going from water to air, this dotted line shows its original path. The other dotted line is the normal line. There will come a point where the refracted angle will reach 90 degrees. Once you exceed 90 degrees, you are right back in the water. Again, this is known as total internal reflection because 100% of the light reflects. You'll notice back here that there is always some percentage that reflects. And you'll notice that as we get bigger and bigger angles, this percentage becomes higher and higher. Once we exceed a certain angle, 100% of the light reflects. Total internal reflection. Okay, here's a great picture of this. You can see the light going straight up, doesn't bend. We can see at a modest angle, it bends away from the normal by a little bit. At a more extreme angle, it bends away from the normal a lot. And at a certain angle, no light is able to escape at all. You'll also notice very little reflection, a little more, and then 100% reflection. So what can happen is if your angles are too extreme, you get your light trapped inside of your material. It cannot escape until eventually it reaches a point where it approaches a surface at an angle close enough to 0 that it can actually get out of your material. Okay, so if we had a light bulb underwater, you can see all the different angles. Straight up gets out. You can see a slightly larger angle, barely refracts at all, more refraction, and then so much refraction eventually that it does not get out. I hope you can picture that this actually forms a circle, okay, in a three-dimensional surface, a circle where light can escape, and beyond that circle, all we get is reflection. Beyond that circle, which is sometimes called Snell's window, because light can escape through it, but beyond that, you get reflection, and it acts more like a mirror. So if you're underneath the water looking up, you can see that circle that you can see out of, but the rest of it, you cannot. If you're in a swimming pool where you actually have some features on the bottom, you'll actually be able to see reflections of the bottom of the pool at those angles that have exceeded the limits of that circle. Okay, we saw how light could get trapped inside that glass block. Well, scientists have figured out a way to use this to send information in the form of light waves from one place to another through a fiber optic cable, which is a cable with a very high index of refraction, making it hard for the light to escape. And you can see how the light, again, bounces around inside the cable as it travels from one end to the other. When it eventually reaches the end of the cable, it'll have a small enough angle that it can escape. Okay, the final thing we'd like to learn is how do we figure out where this angle actually occurs? So we saw, when we watched this, that it's somewhere between 40 and 50, we'll try it again, somewhere between 40 and 50 degrees where the light can no longer escape from the water. How do we get that exact angle? We do Ni sine of angle I, Nr sine of angle R. We start in water. We don't know which angle will trigger total internal reflection. We're going into air, and here's the key. At the highest possible angle, we would have an angle of refraction of 90 degrees. So what we do is we solve for the angle. Sine of 90 is 1 times 1. So we simply do the inverse sine of the reciprocal of 1.33. That will give us our critical angle for light going from water to air. If this was not air but some other substance, we would just change our value to that other substance. Notice that in order for this to work, you need the lower index of refraction to be the one where the light is traveling towards. The higher index of refraction is where the light initiated. All right, so I hope this helps you understand a little better the idea of total internal reflection, Snell's window, and critical angle.